Welcome back. So today we are going to jump into the central limit theorem and kind of the big result from chapter 8. But to get our heads wrapped around where we are turning back to inferential statistics. And we mentioned that briefly back in chapter 1 as one of kind of the main areas of statistics. Overall what we're doing is we are now looking at, so we have a population, we may be curious about certain things in that population, and so to get some insight, we'll often take a sample. Okay, and so what we're going to look at today is this very powerful theorem and result, one of the kind of foundational parts of the way that we do statistics nowadays, the central limit theorem. So we're going to spend some time developing the intuition behind it. And really what it buys us is that we can think about samples from a population, and we can use the tools that we just developed in chapter 7. How do we deal with dealing with normal distributions, percent or likelihoods of being in certain areas along the normal distribution? We can use those methods and apply them to samples from a population. And so it lets us do a lot of very interesting things with sampling and that realm. We can stick with our well-founded methods. So to get there, we're gonna first kind of talk through an example or more of a thought experiment. Okay, so let's assume, or let's think about a good marker. Let's think about so Halloween is coming up. Okay, and I think a lot of communities are struggling to figure out what they're going to do with, obviously kids have a desire to go trick-or-treating, but that's maybe not the safest, having kids going around to different houses and mixing and matching. And so I think people are trying to envision a new way, whether they're sitting out front and just have a bowl of candy and they're sitting outside, although it's pretty cold for that now. Let's say your community has decided to pre-package some candy, okay? And so we're going to put them in little bags. Let me tie it up with a little bow and make a bunch of these bags, okay? And they each have some candy in them, and they range from 2 to 8 pieces of candy. Right, we want to keep some excitement for the kids because then they can open up that bag and see, hey, in this bag I got 4 pieces, and this one I got 7. So the little excitement there. So they range from 2 to 8 pieces. Okay, let's also say that we know that the mean is 4. And your community has made 500 of these bags. And each kid gets to go and randomly select 5. Each kid randomly gets 5 bags. Okay, so some way to keep kind of an excitement, and they still get the candy and all that good stuff. So this happens, it's October 31st. They go through this whole process. Your nephew Timmy shows you his haul from the night. And Timmy has gotten 5 bags. He has a total of 30 what was I gonna, so 38, is that what I was gonna do? Yeah. 38 pieces, okay, for an average of 7.6. So Timmy's bags average 7.6 pieces of candy. So if this seems a little odd to you, then you basically have the understanding of the central limit theorem, or at least the foundational part. Okay? And that's because I think we intuitively know that a sample, and that's really what Timmy has here, right? If this is randomly selected 5 bags, then a sample should, in some sense, be connected or related to the population. Okay, the population here, there's 500 bags. Each of these 500 bags has a value, and they're the mean of 4. And so when Timmy comes to you and says, hey, I got an average of 7.6 in my bags, there's probably some red flags, and you start to wonder about Timmy's future life of crime and how you're going to explain it to his parents, or maybe you're thinking, okay, this is a savvy kid. Maybe I can apply his methods to something more productive for the two of us. Either way, there should be some concern that Timmy's maybe not acting above board here. And so what the central limit theorem gives us is a way to actually quantify and calculate how likely this is to occur. Because Timmy's going to say, hey, I just got lucky, you know. I got 5 bags. They all had a bunch of, 88877 or something like that. I'm a lucky kid. And what the central limit theorem is going to allow us to do is say, okay, but you would have to be, such and such likely, or you'd have to be so lucky. Maybe there's a 17% chance or a 2% chance. We're going to be able to quantify what percent likelihood there would be for this to happen randomly. And so initially we may feel, hey, Timmy's doing something shady, but of course he could be right. We could be wrong. It could have been by chance. But we're going to be able to crunch what that exact value is. So a lot of what we do in Chapter 8 and in future chapters is, we're going to get bogged down into the math and the methods in how we go about this. But overall, this is kind of the base concept is there's something that should be related between the sample and the population. And really, at the heart of the central limit theorem is that the distribution of samples is predictable, and it's related to that underlying population values. Okay, so we'll walk through a little more specific of an example here in a bit. I do want to say, maybe I should just say now, we also know, let me just also say, it's going to be important that we know the standard deviation of the population. So perhaps we know that the distribution, the population has a standard deviation of 1.5. So we'll put that up there for now. We'll come back to it in a little while. Okay. So I'm gonna write down the central limit theorem. Hopefully this is coming through okay. I know Zoom is sometimes a little fuzzy, but if you can't read this, it is in your text. So the central limit theorem, make sure I'm on the screen. And this is really a powerhouse of statistics because it unlocks a lot of what we want to do. It allows us to, as I said, take those methods that we've been working with in Chapter 7 and apply it to some pretty useful scenarios. So the central limit theorem, if all the samples of a particular size, so far for Timmy, we've taken a sample size of 5. So we are now talking about taking all the sample sizes of size 5. If we were to do that from any population, and here our population is those 500 bags. So if we were to take all of the possible samples, the sampling distribution of the sample mean so here the sample mean was 7.6. Timmy's one sample was 7.6. But we would do this many times with all the possible sample sizes of 5. If we put a distribution of all of those sample means, then it's approximately a normal distribution. And that is really the heart of it, is because we know how to deal with normal distributions. We already have those methods to play around with those. One last little part, the approximation improves with a larger sample size. So if we take a larger sample size, instead of 5, we take a sample size of 10, we're going to get a better approximation of a normal distribution. And we'll see that here in a little bit. Okay, so that's really the heart of chapter 8. So let's talk a little bit about this. So all samples of a particular size. So again, we've taken one of these, right? We have a sample of 5. It's Timmy's sample. We're a little dubious about it, but it is one of the possible samples. How many samples are there? Well, what are we actually doing? We're doing 500, choose 5. Right? So there are a lot of these. It's something about 255 billion. Okay, rounded off a little bit. So there are 255 billion samples of 5 bags that could have been made out of these 500. So what we're saying is if we take all of those, and each one of those is going to have an average, right? Some of them presumably would have an average somewhere around 4, maybe a 3.2, 3.7, 4.1. But if we were to plot those all out, the distribution of those sample means becomes a normal distribution. Okay, that's the heart of the central limit theorem. Now, so that's all the samples. It becomes a normal distribution. Notice it says any population. So what do we mean by that? We have some information about the population here. 500 bags, a mean of 4. We even know the standard deviation. We know the range, but we don't know that this is, say, a normal distribution. We don't know that it's uniform. We don't know anything about the distribution. Right? It could be they're just evenly spread out. It could be, I don't know if you can see this, but it could be a normal distribution. Am I off the screen? It could be, some squiggly weird thing. We could have kind of a, and in reality, they're probably something more like that, where it's very defined. There's some bags with 2, there's some bags with 5, a couple bags with 8. Could look anything like these. Any of these are possible. And no matter what, when we do this, it becomes a normal distribution. So we don't have to have a normal distribution of the population. Any distribution will turn into, when we take the sample means, it'll turn into a normal distribution. Okay, so I want to walk through an example of taking all of the sample means. So we've established that it becomes a normal distribution, or that's what the theorem is telling us. But when we think about a normal distribution, what do we want? We want to know the mean and the standard deviation, right? Those are the two things that we need to know and to be able to turn and look at the z-scores and the z-tables. And so if we know the mean and the standard deviation, we can fully depict this distribution. So how do we figure out what the mean and the standard deviation are for our distribution of the sample means? So to get at that, we're going to turn and look at an example. And I'm going to try to not knock this over. I want a little more white space. Let's get rid of some of this. And so we're gonna do a different example, and because we don't want to write down all 255 billion different samples, we're gonna work with a different set. So let's say our population has values 3, 5, 4, and 8. And that's it. We just have 4 observations in our population. Perhaps this is so. Let's say this is the number of pairs of shoes that you and your closest friends have, or maybe it's your roommates. You live with 3 other people, and you're curious about how many pairs of shoes you all have on average. Now, because you're lazy, you don't want to walk into all 4 closets, you're just going to check 2 closets. So randomly, you could select, maybe you select the first and the last number here. And that's your sample. Okay? And what you find then is you get a sample mean of, what is that, 11, so 5.5. Okay, but that's just one of the samples. And what I want to do is walk through all the possible samples that you could have taken. Now, what we're doing here is not done in practice. And I want to be clear on that, because I think when we're learning, specifically here in Chapter 8, we're spending a lot of time thinking about the central limit theorem, thinking about 255 billion samples. But at the same time, you're trying to get your head wrapped around this whole concept of sampling from a population. And so this is never done. We're never going to take all 255 billion. Okay, this is just a thought experiment. If we would have, what would be the result? Similarly, I mean, okay, in this case, you might actually just check all 4 instead of doing 6 samples. But, so know that this should feel a little weird. Why are we doing it over and over and over again? When in reality, when we want to know something about the population, we typically take a sample. There might be certain cases where you'd resample or something like that. But in practice, really what you do is you take a sample and try to get some information about the population. So this is not normal. This is not the process of sampling. The process of sampling is to sample once. But let's say we did take all the possible samples. And again, just to anticipate, we're talking 4 choose 2, which is 4 factorial over 2 factorial, 2 factorial, which should give us 6. You can double check my math there. But we should have 6 possible combinations. So let's work those out. So we did the first and the last. It could have been, we could have randomly chosen 3 and 5 for a mean of 4. 3 and 4 for 3.5. What are we missing? 5 and 4 for 4.5. 5 and 8 for, what is that, 6.5. And 4 and 8 for 6. Okay, I'm going to rewrite these as black just so we can refer to them later. Okay, so there are the 6 different combinations of 2 selected out of 4. Okay, so what I want to build to is, what is the mean of the population? So mu is 3 plus 5 plus 4 plus 8 is 8 plus 12, 20, divided by 4, 5. So I don't know if I'm still on the screen, but we have a mean of 5. So there's a population mean of 5. Now again, we're in a world which is not usually how we deal with populations and samples. If we actually know these values, we don't have to take a sample. So again, this is different than typical, but this is going to lead us to some interesting results. So the mean of the population is 5. Next, I want to know, what is the mean of these sample means? Because remember, what we are interested in is the distribution of the sample means. Right? The central limit theorem is the sampling distribution of the sample mean. Okay, it's the distribution of these samples, of these sample means, not the distribution of the mean, or sorry, of the population. Remember, the population can be any weird shape of distribution. The sample means are going to end up as a normal distribution. And that's the distribution that we want to find the mean and the standard deviation for. Okay, so what is the mean of the, let me do this in red. What is the mean of the sample means? So I'm labeling it as mu x bar, because this is these are a population, okay? We're getting a little, the words are starting to mix in and they can be confusing, but this is a population of all of the possible sample means. So the population mean of the sample means, so the mean of all of these, that's simply going to be 5.5 plus 4 plus 3.5 plus 4.5 plus 6.5 plus 6 divided by 6, right? There's 6 combinations. So we get 9.5, 13, 24, 30. This is also equal to 5. Okay, and that is an important result. And that being, the mean of the sample means is equal to the population mean. So, if we know the population value, here we do, right? Well, in this case, we know it's 5. The mean of the sample means is also 5. So, the mean of the bags of candy is 4, the population. So when we think about all the 255 billion different combinations we could have for samples, the mean of all of those is also going to be 4. So that starts to describe this distribution of sample means, right? This includes all 255 billion, too many to do by hand, but what we know is that this mean is 4 because it is the population mean. So we're halfway to describing this distribution of the sample means. Now, let's pause here and talk about why this is true in general. So we proved it for this one case, right? It just so happens that the mean is 5 and the sample means is 5. But is this always going to be true? Well, one way to think about that is, let me see if I have some different colors. Go back to our observations up here, our population. We have a 3, right? Shows up one time in our population, so it shows up one time over here. When we think about all the possible combinations, different samples we could have taken, it shows up 3 times. We also have a 5. It's just not going to be circled in green. We have a 5. Okay? The 5 shows up 1, 2, 3 times. And the same is true for the other 2 values. So 4, we get a 4, 4, and a 4, and then the 8 is also shown up 3 times. So each of these values that show up once show up 3 times when we think about all possible samples. Now, when we think about 255 billion, they're going to show up billions of times each, but they're going to show up in equal amounts. So each of these scaled up to 3 each of these would also scale up when we think about all the possible combinations. Each observation here has an equal chance, right? This is random sampling, and we have an equal chance, and so they all show up an equal amount. So mathematically, when we think about the mean, here we just applied each value once. When we think about the mean of all of these, it just expands by the same amount. Okay, so they each show up an equal amount of time, but we divide by a scaled up version as well. And so it all cancels out in the end, and we return back to our population. Okay, so the idea that they all show up equally across all of the observations, all the samples, means that same mean is gonna fall out. So that's how we can know that without going through the process of doing all 255 billion, we can know that this process is going to remain, and the mean is going to, the mean of the sample means is going to be the population mean. Okay, so now that's not to say that each sample gives us the population mean. In fact, in our scenario over here, none of these actually spit out 5. So we never got exactly right on the value. And that's something to keep in mind as we move forward as well, in that when we take a sample, we're not under the illusion that we are getting the exact population mean. We're always going to have some sampling error, or that's what we assume. That, in some of these, this is 0.5 off. This one's 1.5. It moves around a little bit, okay? So the sample means move around, and that we can describe in terms of the standard deviation of these sampling means. That is the other part of this distribution that we're curious about. Right, so this is what we want generally, right? For a normal distribution, we want the mean and the standard deviation. In our scenario here, what we really want, or we're going to write this slightly different. We're going to say we want to know the mean of these sample means and the standard deviation of the sample means, right? Because the distribution that we're interested in are the distribution of these sample means, although in this case it's the 255 billion different sample means. Okay, so this is the normal distribution that we want to describe. And so far, we've just found out that we know what this is. It's the mean of the sample means is the population mean. So how do we think about the standard deviation of the sample means? Well, we'll show that answer here in just a moment. To do that, or to get the intuition, we're going to, let's see, I'm going to write these values out on a number line. Okay, so our population, we have 3, 4, 5, and put 8 out here. And our sample means, the distribution is 3.5, 4, what do we got? We have a 4.5. We have 5.5. We have a 6 and a 6.5. Okay, so a couple things. The distribution of the population is wider spread. Okay, it stretches from 3 to 8. We could calculate the standard deviation, right? We've done that 100 times by now. So we could calculate that, but I think we can visually see that it's more spread out than the sample means. So the sample means are a tighter distribution. They get sucked in a little bit. And that makes some sense, right? You can't be on the extreme end, because anytime you randomly draw the 3, you're also going to draw one of these other values that pull it up a little bit from the 3. So it's harder to be on the extreme ends when we think about the sample than it is within the population. So the distribution of the sample means is tighter. We can take that one step further, and remember the central limit theorem talks about a larger sample and how the approximation improves. What also happens is that the distribution gets tighter. Okay, so what if instead we had sampled 3 out of the 4 of you? Okay, kind of a silly exercise, but what are our possible? So 4 choose 3 is just 4 possible combinations. So we can write those down real quick. 3, 5, 4, 3, 4, 8, 3, 5, 8, and 4, 5, 8. I think that's all of them. The sample means in that case would be what? This is 8, 12, so that's 4. This is 7, 15, so 15 divided, that's a number, 5. This is 16 thirds, and this is what, 17 thirds? Okay, so what does that mean? So let's plot these, just for sake of argument. Let's plot these also on this same. So there's one at 4, one at 5. 16 thirds is just a little more than 5. And 17 thirds is in here. Okay, so again, kind of hard to see, but these are more clumped in than even the reds, right? So as we grow the sample size, the distribution gets tighter as well. And okay, so hopefully that's starting to kind of give you a sense as we increase the sample size, the distribution gets tighter. Now, what are we really after? We're after this standard deviation of the sampling means. It turns out, and we won't spend the time to fully derive this. That's a weird looking sigma. That also kind of is, but we won't spend the time to fully derive this. If you continue on with further stats courses, you will definitely come across where this fully derives from. But the result is it's a function of the population standard deviation, which makes some sense, right? If you have more spread out data in your population, your samples are going to be more spread out. But as we've seen, it gets smaller as the n goes up, as we take a larger sample size. And it does so directly related to the square root of n. So in the first case, we had a sample size of 2 was this red distribution. As we went to 3, it's a larger n here. So as n goes up, the standard deviation of the sample means goes down. Okay, so this went to 3, and we jumped up to a tighter distribution in the orange here. So this relationship is how we know the standard deviation of our distribution of sample means. And so now we have a way with our 2 equations to know the distribution of the normal that this sampling is giving us. Okay, so we've worked through that in this kind of silly 4 population example. Over here, though, the results hold true, and we can apply these methods to describe our normal distribution. So okay, so just as a point of kind of notation or what we call things. So this is the standard deviation of these sample means. So the full name would be the standard deviation of the distribution of sample means. We also refer to it as the standard error. Right? And the error, right, thinking about how the sampling error that's going to occur, right? These are not all going to hit. In this case, none of them did, but even in this 255 billion. Almost none of them are going to hit right on the population mean. So there's some error that's happening, some sampling error, and this is the standardized or the standard error. I will oftentimes refer to it as the standard deviation of the sampling means, or the standard deviation of the sampling distribution of the sample means, because it helps me remember exactly what I'm pulling it from. But this is a term you'll see quite often. Okay, so we now have the standard error, and we have a way to describe the mean of this distribution. And so why that's helpful is now all that's left to do is we can apply our methods from chapter 7. We now have a normal distribution, and we know the mean and the standard deviation of that normal distribution. And so we can use our same methods. We can use the z-score, z-table, all of that to figure out, okay, Timmy, how likely is it that you actually found this by chance? Okay, so let's do that. Let's examine Timmy's argument. Okay, so our z-score, I think we might have room if I'm going to come back a little bit here. How does that work? That'd be good. Okay, so our z-score for this case. Now, so far we've used z as x minus mu over sigma. We're going to do the same thing, but notice our notation has changed a little bit. And so in this case, what we're actually after, it'll be easier to do it in a different color. Z, we want to look at the sample mean that we took. Okay, in this case, Timmy took a sample mean of 7.6. We want to see how likely that is to occur. We're going to subtract that from the mean of the sample means, right? This is the mean that we're interested in. Now, of course, this, as we found, it's the same as the population mean. And then we're going to put it in terms of a standard deviation, right? That's what the z-score originally is doing. A deviation from the mean in terms of standard deviation. So how many standard deviations are you from the mean? Same thing here. You're a certain distance away from the mean, the mean of that population. You took a sample mean, there's an error there. Let's put it in terms of standard deviation, but we're putting it in terms of the standard deviation of the sample means, or the standard error. Okay, now you can write this directly as this type of notation too, with just swapping out what we've just done. So you will often see it written this way as well. But of course these are the same, given that we know this equation holds true. So let's go ahead and do it. Let's test Timmy out here. 7.6 minus 4 divided by, so we haven't fully done this equation yet. So let's do it in this form. So we know the standard deviation was 1.5, and we know our sample size is 5. So square root of 5. So this becomes what, 3.6, and I'll just tell you. So the square root of 5 is what, 2.24 or something. This becomes 0.67 on the bottom. And so we get a z-score of 5.37 or something like that. Now, so this is our z-score. That is giving us insight into how far. So Timmy's sample average is 5.37 standard deviations away from the mean. So the rest of the process is the same as what we've done in chapter 7, right? So we know that there's some value out here, 7.6. We want to know the percent likelihood that happened by chance, that's out there. And so what do? We turn to the z-table. Now, as you probably are aware after looking at the z-table enough times, if you try to find 5.37 on the z-table, you won't find it. The z-table ends at 3.1 or 3.09 because at that point, the exact value at 3.09 is 0.499. Okay, so, and this is even further. We could look it up. We could crunch it exactly on either on Excel or online. But we're going to find a value that is greater than 0.4, greater than 0.499, and it's probably 4999 or something. Okay, and so what that means is that there is less than probably a less than 0.01% chance that Timmy would find this by randomness. Okay, so the chance, so basically very few of the sample means are going to be that extreme. Okay, and that's really what we're saying is that there are 255 billion different samples that we could have taken. It is true that some of them would be that far to the extreme, but it is such a tiny percentage that we have reason to be concerned about Timmy's behavior. Okay, and so we may want to think about how do we refocus Timmy's intellect into somewhere that's more beneficial to society, because we're pretty certain that that's enough evidence to say, Timmy's up to no good. Now, I use some terms like use enough evidence or have enough evidence, and that's what we'll return to in the next few chapters as well. Is where do we say this is enough evidence to say, this maybe didn't happen by chance? And so we'll get into discussions of p-values and statistical significance and the like. But for now, it's enough to know that we can use our same z-table techniques. That means we can do other things here with this distribution, right? We now have a distribution where we know the mean and the standard deviation of all of these sample means. And so we can think about all the different kids that are coming here. We can figure out, how many of them are going to be in certain windows. We could figure out how many of them are going to go home crying because they had an average of, less than 3. We can figure out, what share of them we're going to be concerned about diabetes because they got too much candy, and the like. So we can do all of the more complicated scenarios that we covered in chapter 7 of taking 2 z-values and finding the areas and subtracting off and finding the likelihood of being in between certain values. So we can do all that in this sample distribution scenarios. So that's where we get to in chapter 8 is being able to play around with this. Now, again, I want to point out that a lot of what we're doing here is not the end of the story. It's not what we typically see in sampling. This is a lot to set up what we're going to do in the next few chapters. Like I said, we never take all of the samples. Furthermore, we don't often, now sometimes we do, but it's not always true that we know the population mean, right? In Timmy's case here, we did. And in fact, in this scenario, we might know this because we put the bags together, for instance, right? So there are cases where this is true, but a lot of times we don't know the mean, right? So if we're thinking about, you want to know the average income of people in the community, you take a sample, you don't actually know the average income yet, so you use the sampling to try to find a good estimate for that sample or for the population. Similarly, we don't know if we're interested in the state of Minnesota and who they're going to vote for in the next election. We don't know the answer. We don't know the share that are going to vote for Biden. But if you take a sample, call a bunch of likely voters, you can get a sense as to where that mean might be. So it's a little different process than what we're showing here. So a lot of times we don't know the mean, and a lot of times we don't know the population standard deviation. Again, in this case, we do because we put the bags together. But when you're calling up likely voters, you don't know the standard deviation. So we are going through the Z calculation right now, knowing the population standard deviation. And where we turn to in, I believe we touch on it right away in chapter 9, is what happens when we don't know that. Okay, and there's some pretty easy fixes for it, but we're going to have to tweak this method a little bit. But the overarching concept is still housed in this normal distribution and how we can play around with it. Okay, so a lot of where we're going are just slight deviations from this general process. Yeah, and again, this general process, a normal distribution spits out here from what doesn't have to be a normal distribution. So we can apply our methods, we can apply those very specific methods from chapter 7 to scenarios where the underlying population is not normally distributed, but the sample means are. One last thing. So we do know that the approximation improves with the larger samples. So I'm not going to draw it here because it'll be my art skills won't allow it. But the text has a very good infographic about there's 4 distributions, some of which are kind of crazy, some are uniform. And as we increase that sample size, the distribution becomes more and more normal. And in fact, we'll see this on Friday, likely in Excel. We'll play around with some stuff. The other thing that happens, though, and we saw that over here, is that as the sample size gets bigger, the distribution gets tighter. Okay, so if, for instance, we had let all of the kids take 10 bags instead of 5, our sample size has gone up. And I don't know if you can see that, but it's a tighter distribution. Okay, and what does that mean? It means now if Timmy says, oh yeah, I got 10 bags and I still got an average of 7.6. Okay, we already thought he was lying, but now the likelihood that that's occurred has gotten even smaller. Okay, so again, it's harder to get on the extreme ends when you have a larger sample. So when we increase the sample size from 5 to 10, it gets tighter. In these extreme cases of an average of 7.6 are even less likely to occur by chance. So that's kind of 2 things that are happening when we increase the sample size. Number 1, it's helpful because it does give us a better approximation of a normal distribution. It's a little cleaner. And then number 2, it gets a tighter distribution, which is something that we haven't talked about the methods of sampling here today, but when you think about running a sample, right, it's a different, you can be more sure about certain things. Say for instance, we're curious about the election, and you call up 100 people, 100 likely voters in Minnesota, you can get some information. If you call up 1,000, you get more information, right? It gets a tighter distribution. And we'll talk about, again, in this case, we don't know the population mean, and so what we're really looking for is trying to narrow in on where that population mean might be. So sample size does a few things for us. Okay, so yeah, I think we'll leave it with that. We'll talk more on Friday. We'll walk through some examples, and I think we'll play around in Excel and see this a little bit in action. A couple other things to note. So this is chapter 8. Next week we'll cover chapter 9, and again, that's going to play around with some of these when we move away from all these nice clean answers to everything. And then we do have the second midterm coming up at the end of next week, or after next week. It'll be the same format, same style, and on the syllabus, it's currently it'll be that same. It's set up to be that same Sunday to Tuesday. Now, what I'll probably do is shift that earlier a little bit because I don't want everybody feeling like they need to cram through their exam on election day. So I will give it to you earlier and have it due at least earlier in the day, if not the day before. So I'll touch base with the exact value or exact dates, but know that that's coming after Chapter 9 material. So if you're having confusions or struggling through this, please let me know. Reach out to me. Come to office hours. I'll be on office hours in a little while today and then again on Friday. But please stop by and we can talk through some examples, or if you have questions about some of the homework problems, we can do that. So yeah, but better now than when the exam has come and gone. So yeah, with that, we'll talk to you soon.